time, so let's just get started. Any questions on anything that we have seen so far? Any feedback? We haven't really done.
I don't have questions, so I look at the homework.
Well, you will have a lot of questions when you do the homework.
I've already looked at it.
Particularly about Matlab, I think,
Yeah.
if you haven't done that. Matlab?
A lot of people actually like go versus like do it and it's take us forever. Like maybe like for our first time you just like show us a little bit what we're in the field of thinking and stuff.
I am going to do it today.
It's
part of.
there are some people that really like never been. Yeah.
Yeah, yeah.
Some people just like do it and like probably how to use programs.
It's part of the lecture today. I must apologize. I would have preferred to put the notes well ahead of time, but I still make changes in the last minute during the previous night before. So the lecture notes for a particular lecture will be up by 8 a.m. in the morning. That's what I'm trying to aim for. Okay. So if you get a chance and you want to print it out before you come to the class. If not, you can always download it later, take whatever notes that you need. And in the lecture notes today, I have a place where I'm going to take time and do a Matlab demo. Okay. So after this lecture, you should be able to do the first assignment. It is going to be somewhat of a challenging assignment if particularly you get computers.
We're all in the computer lab printing out the notes because they weren't printed or they weren't posted until late this morning.
Right.
And also I noticed that when I print out the notes, sometimes we'll have different notes on the board. Can you keep them the same?
It will be the same. It will be the same as long as you print out the lecture for that particular. Let me just explain what I'm doing, how I'm working, and I would like to address that issue, but I need to be a bit more organized for that. This is the Moodle page. When you log into the Moodle course page, this is what you will see. And you will see for every week the content for that week. Okay, so that is a lecture notes, which will be the PDF file. And that is the file that I will be using in the class. Now, if you look at the end of that lecture notes, I might have some material that I haven't covered. And I'm going to cover it in the next class. So the notes in here will be slightly different because I'm kind of revising it the night before. Okay? So, but for lecture 2, this should be up by 8 a.m. on Moodle. And that will be the notes that I will be using, not the one from there. So if you print it out from the first notes, first lecture notes, a little bit of it, if you're looking at that to compare what I have, then maybe slightly different, not very much. But I will try to put, I will always post it by 8 a.m. from the day of the lecture. How many of you think that is still a problem? You prefer to have what?
I have class at 7:30.
Okay.
So I'd be out of class.
Okay. How about 8 p.m. the previous night? That help? Okay. I will aim for that. I cannot always promise, but I will aim for 8 p.m. the night before. And if you can print that out and bring it, that will be the lecture that we will be following in the class. Okay? And after that, you have a recorded version of the lecture. And some people have already had difficulty in making it work on your computer. Has there been any success story? Anybody been able to? It works fine? You have Windows Media Player. Yeah. This is a mic that I'm using. I particularly, if I go towards the board to explain something, this picks up nothing. Okay, so I have to stay close to this, and that's why sometimes I try to kind of doodle on this, hoping that you can pick it up from there instead of going through the board. I'm not sure exactly how to improve the sound quality, but that's the current technology that I have. The recording is in Windows Media Player format, and so you need a Windows Media Player installed on your computer, whatever it is. And these are fairly large files, about 100 meg each lecture. Okay? So if you have a slow speed connection from home, you may have a problem. And I can try to put it somewhere else, or if you want to bring once a week pen drive, I can copy it for you if you cannot download it. Okay? But once you click on that, what should happen is it should open up a new window like this, and it will buffer, and depending on the speed, that might take longer. This is now wireless, so this is taking a while. In my office, I've checked it out and it works okay because I have a wired connection much faster. While it's downloading, let me also tell you that I have put the first assignment up this morning, and I've given you a week to work on. And once I finish the lecture today, you should be able to get started on that. And feel free to drop in anytime, particularly if you have problems with Matlab. With Matlab, my suggestion would be, I will go through the demonstration today on how to start Matlab, how to do little things there and there. Files that I use in the class. I haven't plugged it to any speaker system. I can hear it, but you cannot. Okay, so you need a speaker attached to it. But that's basically what you should see. And then there is a slide bar here. So you should be able to slide to any position, but it will buffer once you do that. Okay. Please don't buffer. Any questions on that? If you have any specific questions with pure computer configuration, please drop by in my office and I can try to diagnose what the problem is. And IT people should also be able to help you with that. Okay? So that's for last lecture, and for this lecture today, I have put the first assignment, which is due next Monday by 4 p.m. Okay? The problem is an extension of the problem that I'm going to do today. Okay, so hopefully slow me down if I'm going fast in today's lecture. This lecture is important. A lot of things are needed here. Okay, any questions or comments? Not yet, yeah. All right. So just a quick review of what we did in the last lecture. We basically looked at a steady. The question that we tried to answer in the last lecture was how do we set the optimum set points for a plant? Okay? And we illustrated that using wastewater treatment plant, and we said that you can pose it as an optimization problem under steady state, and then find out what the operating conditions are. So that's going to be your goal. That's going to give us what we call the set point in the control system, so that we can then drive the system towards that set point, towards that optimum operating condition. And if the plant has a tendency to drift away from it, we want to take control action to put it back into that particular operating condition. And in order to do that, we saw that we also need a dynamic model, a model that captures how a system will respond if I make a perturbation, because the disturbances are always there, or in some cases I may actually want to change a specific flow rate or temperature. So in this lecture we're going to talk about building a dynamic model. Okay? So the problem is the water heater tank. Okay? So you have water coming in at a certain flow rate in terms of kilograms per second, and at a certain inlet temperature, say degrees Fahrenheit. And it's being agitated well, so we are assuming that the temperature inside the tank at any point will be the same. And we are adding energy, Q, from an electric heater, for example. So that's going to increase the temperature from Ti to T. Now, in this problem, we are saying that the outlet flow rate is the same as the inlet flow rate, and there is no disturbance in the piping system, that hydraulic system that feeds the water, for example. So W is the same at the inlet and outlet, so the level is constant. It doesn't change with time. The problem that you're going to look at in the assignment is one where you allow the height to change. Okay? So we are going to allow the outlet flow rate to be different from the inlet flow rate. So I make a change in the outlet valve setting, but I don't change the inlet valve setting. Then the liquid will accumulate. Either it will decrease or increase, and you need to write a mass balance equation for that. What we're going to do today is get away with this mass balance, saying that the level doesn't change, inlet is equal to outlet, mass balance is always satisfying, but inlet energy is not equal to the outlet energy. It is inlet energy plus whatever that we add to the heater is equal to the outlet energy. Okay? So that is a physical description of the problem. And our task is to develop a control action that will manipulate the amount of heat that you add so that no matter what happens to the inlet temperature, decreases or increases all of a sudden, I want to maintain the outlet temperature at a constant value. And that I'm going to call as TR, would be my set point. Okay? So I want to increase the temperature from TI to TR, and if there are heat losses, if there are perturbations, disturbances on the system, I want to adjust my Q continuously as a function of time, monitoring what the outlet temperature is. If the temperature goes down, I increase the heat. Temperature goes up, I decrease the heat. So I'm manipulating the heat flux Q to bring the temperature to the set point. Okay? So I'm assuming that the temperature inside the tank is uniform, and the T, the outlet temperature, is always greater than the inlet temperature. Of course, if I shut off the heater, the outlet temperature is going to be the same as the inlet temperature. Nothing really interesting happens. Okay? So I'm going to write a steady-state energy balance equation. Steady-state energy balance equation says input equals output. In general, any conservation equation is rate of accumulation equals rate in. This you are very familiar from previous courses, minus rate out, plus rate of generation or destruction. Okay? So this is the concept of a conservation law. And in this particular case, because I'm saying it is steady state, there is no accumulation of energy or mass in the system. Okay? So rate in equals rate out. Okay? And we saw towards the end of the class, when you write that as the rate coming in is WC times TIS. Whatever the energy, MCPT, okay, whatever the energy that is coming in with the inlet stream, plus whatever energy that I'm adding to the heater, minus whatever energy that goes out, which is WC times TS, the outlet temperature, that should be equal to 0. There is no generation other than the heat addition itself. So this is a statement of energy conservation law in the control volume, which is the tank itself. Okay, any questions on that? All I've done then is rearrange that equation by writing as QS equals WC is a common factor, and I write it as TS minus T when it takes it to the other side. So this gives me the steady state balance equation, okay, energy balance equation. Okay, so under normal operating conditions, the outlet temperature, the steady state temperature TS, will be what I require it to be, TR. Okay? So I'm making a subtle distinction between TS and TR. TS is the steady state outlet temperature. It could be anything depending on QS, whatever I put in. But if I want it to be TR, then I need to calculate. Okay, so for example, I give you the flow rate, I give you a heat capacity, and I give you the inlet temperature. And then I say, I want the outlet temperature to be 80 degrees. The inlet temperature is 45, I want the outlet temperature to be 80 degrees. As a design engineer, process engineer, what you should do is calculate what is the amount of heat that is needed to raise the temperature from 40 degrees to 80 degrees. So in this equation, this will become the unknown. Okay? So you set the target point, and you are given all the other conditions, the inlet temperature, flow rate, etc. You calculate what should be the heat duty that will achieve that task. Okay? Now, if understood all this, I have a question for you to think about. Okay? So the tank is operating under steady state condition. I'm putting in QS, a certain amount of heat, and the temperature outlet is TR, under steady state condition. All of a sudden, at this time, I come and increase W, increase the mass flow rate, keeping the heat rate QS the same. What do you think will happen to the outlet temperature? It will drop, right? Intuitively, we are able to see that. Now, this equation should be able to explain why that is and by how much. because you're keeping Qs constant, right? And you're keeping C constant and TIS constant, inlet temperature. You're saying that I am, what did I say, increase W. So if I increase W, what should happen to this term? So that the product is the same as Qs before. It should decrease, right? And that means if TIS is constant, TR must decrease, outlet temperature decreases. So this equation gives you the steady state relationships. If you ask the question, how long does it take to recover back to the original temperature, that would be a dynamical question. That's where we need a dynamical model. The steady state model tells you the consequences. I increase W, TR should decrease. Okay? So this should decrease. Similarly, if TIS increases, what should happen? That is, the inlet temperature increases, but the same flow rate. Same flow rate, same QS, I'm increasing inlet temperature. What should happen with outlet temperature? It should increase, right? And that again will come as a consequence of looking at this equation. QS is constant, this is constant. If I increase this, I should increase by the same amount so that the difference is constant. Because W is constant, so the difference in temperature cannot change. So you can actually tell, if I increase the inlet temperature by 10 degrees, you can predict the outlet temperature must increase by 10 degrees also. Okay? So those type of questions are answered by looking at only the steady state model. Okay? Then you can ask the question, how can I adjust QS in such a way that the outlet temperature will go back to PR? Whether I put a perturbation in the flow rate. When I put a perturbation in the flow rate, in this case I'm saying that the flow rate is changed both at the inlet and outlet at the same time. Okay? Because I just still don't consider that level change. That's what you're going to do in your problem. So if I change the flow rate or if I change the inlet temperature, what should I do to bring the temperature back to TR? How would you answer that question? All you need to do is you take the original TR that you had, to put that in here, use the changed W, and recalculate what the heat duty should be. And then go and manually adjust the heater. Okay? So that it will bring it back to whatever the original temperature is. So the same equation, the things that are specified are changing on you. So that you can look at the consequence of how it changes, how you can restore it back to the condition. Any questions on that? So the next question is, how long will it take to get back to the old set point? What should I do to get back to the old set point is answered by the steady state part, increase or decrease the duty. I can calculate what the duty should be. But how long does it take to reach that new steady state? You need to look at the ability of the liquid to store heat, the heat capacity term. Okay? So you're now making the rate of accumulation, rate in minus rate out. So generalizing that energy balance that we did before, and I'm allowing for this Q, the heat flux into that heater to be a function of time, because that's what I'm going to manipulate. Now, is everybody clear with that equation, or you want me to write it down and develop it? Is it all okay? All right. So that is the transient balance, and this term is called the heat capacity term, ability of water to store heat, rho V times C. Cp is the specific heat. Okay. So this equation, of course, should go back to the steady state equation if you say that the temperature change is 0. So I drop this one. Then Qt should go back to Qs, the steady state value, and T should go back to Tr. So the dynamical equation will give you the steady state value in the limit as T goes to infinity, for example. So if I'm able to solve this equation, we're going to see how two ways. One is analytically, other one is numerically using Matlab. And in the second problem, the assignment problem, we are going to do only by Matlab, because now we have two equations to deal with. But what we are looking at by dynamical is I'm plotting T as a function of time. So if I increase the temperature, the system is going to respond something like this. It's going to take a certain amount of time before it reaches the new steady state. Once it reaches the new steady state, temperature change with time, the dt will be 0. That is, derivative of temperature with time will be 0, and the steady state condition. So the temperature will be flat. And then, of course, this term drops out, and you get back to a steady state solution. Okay, now we're going to ask the question, okay, how do I develop a control strategy? A strategy that allows me to take an action as long as the measured temperature is not the same as the temperature that I need, the set point. Okay, so the control scheme, this is the control system design. As a control engineer, this is what you're doing all the time, understanding the process, developing a process dynamic model, identifying a variable that you can manipulate mathematically now, okay, and then coming up with a control scheme which says this is how you should manipulate this variable. Now, what are we saying in this equation? This is not a mass balance or anything. Can you interpret? If you see something like this in your book, I want you to be able to kind of explain or understand in your own mind. What does it say? What does the equation say? What is this term, WC times TR minus TIS? This is something that we have already seen before. WC times TR minus TIS, right? That is the amount of heat duty that I would need under steady state conditions. So this is the same, this entire term is the same as QS. Okay? So what I'm saying is that the amount of heat that you have to put in is going to be what is required under steady state conditions, plus a correction that depends on what? It's going to vary with time, obviously, right? But what is the meaning of this term? We talked about it in the first or second lecture. What does that term tell you? It is the error. It is the difference between the actual temperature and the set point. Okay? So if T goes to TR, that difference is 0. So all you're going to input into the heater is the steady state value. So the error goes to 0, right? But if the error is different from 0, meaning T is different from the set point TR, then you're going to say, I'm going to add a certain amount of heat that is proportional to that error. Now, Kc is called the proportional constant. Okay? So of the PID controller that we talked about, proportional integral derivative action, this is a proportional controller. So it controls the system based on an error that is a control action that is proportional to the error. Control action is this term, it's proportional to the error. Okay? So we take this QT. This is one of the reasons I guess I don't write my hand. Pretty soon it gets very cluttered, but I hope you are able to follow it and you'll have at least a clean set of notes. Okay? So what we are going to do now is take this QT and plug it in there, into the dynamic model. Okay? So this is the dynamic model. This entire thing is a dynamic model. And into the dynamic model, I have a control scheme that I have written down, so I'm going to replace that. When I do that, I get the next equation. This is the energy balance equation with a very specific control scheme. And that control scheme is the proportional. Okay, question, yeah.
Can you define the difference
Set point, that is a set point. T is the actual temperature in the tank. And that is the temperature that appears here, because that is the accumulation of energy depending on what is the current tank temperature. This is the same temperature, because that says how much of energy is coming up. Coming out at the same temperature as in the tank, and that is the same temperature. The T is the unknown variable here, and that's what we are going to solve for. When I say find the solution T as a function of time, I want to generate a graph of how that temperature in the tank is going to change with time by solving this differential equation. And everything else in the differential equation is known values. Okay? Rho, the volume of the tank, the heat capacity, density of the water, inlet flow rate, heat capacity, inlet temperature, TR, and the TR is the set point, the desired. So when T reaches TR, this term will drop out. And then again, and this term will drop out because it's a steady state, that changes, and I will get my original steady state equation that I wrote down. So in this part is the original steady state part. So the control action stops when heat reaches TR. Ti is the inlet temperature. TIS is the steady state inlet temperature. If it doesn't change. But I could change the inlet temperature to something else. So that will be a forcing. I can change the inlet temperature from 25 to 25 degrees and then ask what happens to its process. Okay, any other questions? Kc is the controller gain. That's what we need to design. We need to find out what is the best value of Kc. So we need to have some sort of a target. And once you look at the solution, you will understand how to pick Kc. What are the problems in choosing Kc? Okay. So as a control system engineer, these are actually knobs on the controllers. When you go to the plant, you will find that, of course, these days it's all digital. In the older plants, you will actually have knobs that you can set the controller gain. But nowadays, you will enter a value in a computing to set the controller gain. So far, everything we have talked about is conceptually understanding the problem and posing it as a mathematical problem. Now, you need to call your differential equations. I'm not going to really develop the solution. I will show you how to do it in Matlab later on. Okay? But all I'm doing in going from this step to this step is just manipulation, algebraic manipulation. I'm dividing throughout by WC. Okay, so the C cancels out and I get rho V over W. And I'm collecting all the time terms, the temperature terms that I pointed out. This one and this one. Okay, they come to the left-hand side. So here I have 1 plus Kc over WC. Again, all these are known except for Kc, we need to tune. And on the right-hand side, I have all the known quantities. The inlet temperature, the set point, and the heat duty, etc. So this is an equation in this form, tau1 times the rate of change of temperature to the time, plus a constant A and C equal other constant. What you should be able to do in assignments and in an exam, I guess I will give you the template. I don't expect you to really remember how to solve differential equations. Okay, this is not a course about differential equations, but you need to be able to use the results. Okay, so I'll give you a formula sheet, and if you see this differential equation, you should be able to write down the solution by looking at the template. Okay, kind of a pattern matching, but more than that. Now, the term tau, which has rho V over W, if you figure out the units, what will be the units? Let's figure it out. Rho has the units of density, so it's going to be kilogram per meter cube, and V has the units of meter cube, so that has the units of kilogram in the denominator. W is flow rate, kilograms per second. So what should be the units of the whole thing? Second. The second is in the denominator of the denominator, so it goes up, so it's going to have simply the units of second. So that is called a time constant for the model. Okay? So it tells you how long will it take. It actually, without solving it, it tells you approximately how long it will take for the system to go towards a steady state. Okay? Roughly of the order of, if this comes out to be 2 minutes, it will be roughly of the order of 2 to 4 minutes before it reaches new steady state, whenever you make a changes. Okay? So that's an important terminology that you should know, because we'll be using often. The time constant for this process is second class. You should know what it is. Basically, it's actually multiplying the rate of change with respect to time term. Okay? And A and B are, of course, constant. And what we are going to do is we are going to look at different scenarios there, and this is in fact what you're going to do in your assignment too. What happens if I change the inlet temperature from the current steady state value, TIS, by a certain amount? Okay? So I'm increasing the inlet temperature by 10 degrees or decreasing the inlet temperature by 10 degrees. How does the temperature of the tank, this T, changes over a period of time? Okay? So for T less than 0, it's been at a steady state. So what we are doing is graphically the following. This is a temperature axis and the time axis. Initially the temperature is at TIS. At certain time, T equal to 0, I'm increasing it to TIS plus delta TI, the inlet temperature. We increase or decrease. Okay, I'm changing it. So the system has to respond, and the response could be something like this. That response is determined by the solution to this particular problem. That's what we're going to do. Okay, the solution to the differential equation is given by this expression. It's an analytical solution. How does the temperature change with respect to time? Okay, And you can see that there is 1 minus an exponential term. All these are numbers that we can determine, we know. Okay? So here is t. So what happens as t goes to infinity, to the second term? E to the power minus t something. Okay? Because of the negative sign, as t goes to infinity, the exponential term will what? It will decay. Right? E to the power minus 1, e to the power minus 2, minus 3, etc. is going to be going down to 0. So e to the power minus infinity will be 0. Okay? So the second term goes to 0, basically giving back to you just 1. Okay? So it is a set point plus a correction that is going to occur to bring it back to the new set point that we need. So if you plot this particular equation in Excel or whatever, you're going to get curves like this for different values of Kc. If I set Kc equal to 0, that means there is no control action. Okay? Then if I increase the inlet temperature by delta Ti, what is going to happen to the outlet temperature? It's going to be Tr plus delta Ti. So the temperature will rise towards that particular value. Okay? And you can answer the question of how long does it take by simply reading on the x-axis. Now, if I increase Kc, the controller tuning parameter, I set it equal to Wc, for example. The reason I picked Wc is that it cancels out. Wc over Wc is 1, so I have delta Ti over 2. Okay? What I find, this is an interesting thing, what I find is that the temperature of the tank will go and reach a new steady state, but it will not be the same as Tr plus delta Ti. And this is what we call an offset. Proportional controllers always have this offset. You cannot get it back to the set point that you would like. Okay? There is always an error, and this is why we need other actions, because we just made up the proportional rule, and we find that it can help you in one thing. For example, if you take 3 times Wc and make the proportional constant really very large, what am I saying when I say Kc is very large? If you go back to this particular equation, if I make Kc large, what am I saying? I want to add a lot of heat even when the error is very small. This is the error, right? So the proportional gain simply says how much of heat you want to add even when there is a small error. Okay? So by increasing the gain, I'm saying add a lot of heat very quickly, so the response is very good. Meaning, it will reach, for example, if it took this long to reach steady state, it takes only this long to reach a steady state. Okay? So it reaches the steady state quickly if you have a high proportional gain, but the value is not the desired one. Okay? Any questions? Am I going fast? Okay. So when Kc is 0, no control action, then Ti increases by delta Ti. The inlet temperature increases by 10, the outlet temperature will increase by 10. Okay? There is an offset from the desired set point if Kc increases away from 0. So that is a problem with the proportional controller, which we can solve with the other controllers. And if we do not want Kc to be very large, because then it amplifies the errors. Okay? And it can create something called unstable system. So we will see what the unstable system is later on. So let's go to Matlab and see how I would implement this particular model in Matlab. So the way to start Matlab in your computer room next door would be to go to the start button, and then, or maybe on the desktop you may have a Matlab icon. So just click on that, and that starts the Matlab session. Matlab, for those who are not at all exposed to that, is an interactive programming environment which has a lot of mathematical toolboxes built into it. So this course we will be using quite extensively. Okay? So what would happen is you would get a desktop environment like this. There are several windows in there. For some of you, this may be very boring. For some others, it may be very fast. So you need to control my speed. Okay? So there are several windows that you see. The most important window for us is the so-called command window with this prompt. Okay? So you can go and enter any command on that point, and it will immediately parse that, analyze that, and respond to it. For example, if I type A equals 2, all it's going to do is create a variable called A, assign a value for 2. Okay? And if I just type A, then it says its value is 2. So it has something called a workspace, and in the workspace you define variables, assign them values to it. Okay? For example, I can say sine of A. What do you think it will do? It calculates sine of 2. What has happened is, at this stage, when I type sine of A, it already knows the value of A. Then it says, what is sine? What does he mean by sine? Okay, so it passes through that and says, okay, sine is a built-in function. So the function has an argument. The argument is A. So it takes that value, passes the control to the sine function. The sine function says, okay, I'm going to calculate what is the output. And it echoes the output for you here. Okay? So this is how you would use function. You can build your own functions in Matlab. Okay? And to solve problems, you need to be able to build your own function. Now, there are a number of other windows that are useful to know. One is called the current directory. Okay? So this is a directory in which I have all the files. Now, of course, this is pointing to the wrong directory. So if you want to change to a directory where you normally work, you'll go to this place and choose the directory to be the one that you want. So in my case, I want it to be, for this particular lecture, where do I have it? Courses. Lecture 3. Okay. So I'm selecting Matlab, say use this as a current directory. So immediately it goes in there and you'll find all the files in the directory, the lecture notes itself, and then there are two functions. These are called M files. You can edit, you can create them, and it will open it pretty soon. But this tells you what are the files in your current directory, and if the file is there, it can actually act on it. For example, if I say type htank. So htank was a function that I built without this particular problem. Here it is. It's called htank.m. So when I type that, it says what is in the particular file. These are all the statements in the file. We'll decode each one pretty soon. Okay. So what this function is going to do is take a certain input for time t, lowercase, and certain input for temperature t, capital T. Take these two numbers, goes into that function htank, just like it went into sine to the value of 8. Takes these two numbers, goes into the function htank, and then does all the calculations that are supposed to be done. These are all the statements. And the last one is f equals. So it calculates what the function value is and returns that function. So the structure of a function is going to be like this. You have the first statement of the function should always be a keyword, call function, space, and then all the outputs that you want from that function to be returned to whatever program that calls that. Okay? And then equal to some name of the function, you can call it anything you want, and then the input arguments. So these are called the input arguments, this is called the output arguments. Okay? For example, to execute that function, all I need to do is type the name of the function, htank 0, 45. So what I'm doing is, question please. Am I talking too fast? Is there a question? Or? Okay. Please do stop me, okay, if I'm going too fast. It's going to take these two numbers, 0 and 45, assign lowercase t to 0, uppercase t to 45, and then go into that function and substitute these numbers and calculate all these, assign all these values and calculate the last function f and return that. So that f is nothing but the function that we saw in the dynamic model. You'll see term by term, we'll compare it. So it returns a value of 0.16. Okay? Now, I'm going to ask you a question. How do let, oops. I will explain what it is, and then I will ask you what you think it will do. So in Matlab, my fingers are not. In Matlab, if I type something like this, maybe let me ask you to guess. What am I trying to do there? Range of values. I'm passing for temperature. For time, it's just 0. For temperature, for the second argument, I'm saying, take a range of values from 45, 47, 49, all the way up to 50, and return the values for the function for each one of them. Okay? So between 45 and 50, in terms of 2, you will have 45, 47, 49. So for each one of those values, these are the function values. Okay? So Matlab has calculated all the three functions, function values, and returned it to that. There are a few other windows here. Matlab is really a big ocean. Okay? So this is just the first step, baby step. As I keep repeating to all my students, I don't know more than 10% of Matlab. Okay? What is important is to have the curiosity and to learn as you need. Okay? So here we have a workspace. The workspace simply stores all the values. Yeah, please. 49. That's a good question. So if for example, you can do this. If you just type, what do you think it will do? 45:2:50. It just returns all those numbers. Okay? So if you are in doubt, what is it going to return? You can try this. For example, if I do 51, what do you think it will do? It will have 4 values including 51. Right? So that way you can quickly decide what it is going to send to that calling function. Okay? So if I say, for example, t equal to this, what is going to happen to this workspace array? See carefully. Now, previously, it just entered the numbers, output the numbers. Now it's creating the numbers and sending it to a variable t. So t has a value of 51, and t appears there in the workspace variable. Okay? So t is now a variable available in the workspace, so you could do this. Okay? So t is going to have all those 4 values, and will return 4 values. You get an idea, roughly, of what Matlab is able to do? Okay. And then here you have a command history. A command history is basically all the commands that you have typed. You look carefully, these are all the commands that we have typed. Okay. You can use them, you can call them by scrolling the up arrow key. You can recall all the previous commands and edit them if you like, etc. But let's open up that. By double-clicking on this, we're going to be able to open that particular file. So this is a separate window called the Matlab Editor. And this is how you write a function. All it is now is a text editor. So just go and write whatever you want to do there. And there is another function called eg1. So this is another function I wrote. So there are 2 functions I have opened. H9 and eg1. What is going to happen is eg1 is setting up the problem to call Matlab ordinary differential equation integrator, and then that's going to call the HTAG function, and it's going to give me the solution to the particular problem. I will put both these M files on the workspace, on the Moodle, so that you can download and play with them. So what does this do? This has only 2 lines. The first line says a variable called options, and ODE set is a function just like sign. Okay? Matlab has tens of thousands of these functions. This is why you cannot really master everything, but you should be able to look it up as you need. Okay? So ODE set is a function which says output function. What is the output going to? From this particular function. ODE45 is another function. Has anybody used ODE45 or anything like that in the past? This is nothing but an ordinary differential equation integrator. What that means is, if I have a differential equation dy dt equal to some function of y and t, this is an ordinary differential equation. The Matlab ODE45 is going to take this function and give you the solution for y as a function of time, a graph. Okay? So that is the purpose of ODE45. The numerical method shows you will understand why or how it does all those things. For our purpose, what you need to know is that this ODE45 takes the problem that you define. So this one says the name of the function problem I want to solve is HTAG. So in your assignment you will create another function, okay, and that will be the name that you will use here. And then the second argument to ODE45 says start from 0 and go up to 20,000 seconds. So that's a range of time on the x-axis over which I want to get the solution. And the third argument is The fourth argument is the options, which is set by the options program. And the third argument is, I don't know what it is, I forgot. Okay? So if you forget, what do? So you go back to Matlab environment, okay, and type count ODE45. This is very important, how to get help and how to interpret the help. Okay? So it gives you quite a bit of information about ODE45. ODE45 is solving non-stiff differential equations. Now, we need to know what a stiff differential equation is, right? But we will not worry about them. What I want you to understand is the first function is the name of the function that you are going to solve. Okay, name of the problem. The second one is the t-span, for how long in the time domain you want to integrate. What should be the third one? Initial condition. Because when you are plotting, let me go back to this, when you are generating a solution like this, y as a function of time, you need to know what is at time 0, what is its value. Only if you know that, you can start integrating it from there. So the initial condition, I shouldn't have forgotten that because it's an important parameter. How these things happen, right? So y0 is the initial condition for that particular problem. Okay? So going back to this, the initial temperature is 80 degrees. Okay? In the tank, the initial temperature is 80 degrees, and I want this problem to integrate from 0 to 20,000 seconds and get me the profile, and it returns the time value at which every temperature is calculated. So it's going to calculate from 0 to 20,000. It's going to determine the time step automatically. Okay? So we will look at what the solution looks like. Any questions so far? Am I going fast? The options is the one that sets what should, for example, the output function should go to a plotting routine so that we plot the temperature profile. The first option says ODE output function is ODE plot. So it transfers the data for T and T, capital T and lowercase t. Lowercase t as the time. Remember, to go back to this, what we're going to get is, we're going to get on the time axis a series of data points. Okay? And the T vector will contain all the time values, and the capital T vector will contain all the temperature values. Good question. I already have in my workspace a variable called T. So what will this do is your question, right? No, it will just overwrite it. Overwrite it. So whatever comes out, that's a good question. Whenever something is appearing on the left-hand side of the equal sign, it's an assignment. So it's going to assign to that lowercase t and uppercase t the value that is returned by ODE45. If your workspace already had a t defined, it will be lost. Okay? Any other questions? Yeah. Yeah, sorry. That's the second argument in that. Relative tolerance. It simply says what is the error that I'm able to accept in the temperature profile. Okay? The temperature profile should be accurate to about 6 digits. Accurate, for example. It uses that information to find what the time step it should take. This is a numerical methods question because the error depends on the time step that you take. Okay? So here all you're saying is give me an accurate solution. Okay? So how do I run this? To run this, I can go to this green button there and hit the green button and I get the solution. Okay? So what this is the temperature on the y-axis, time on the x-axis, 0 to 20,000, and that's how the temperature changes. Changes very quickly. Maybe in 500, certainly less than 500 seconds, and then it's reaches a steady state. Okay? So in your current assignment, what you need to do is take these two functions and change. First, develop the dynamical equation. The same problem now I'm allowing the levels to change too. So you need to write the mass balance. So we'll have two equations. Okay? And what that will do is when you go to this function, you will not just have f, you will have f1 and f2, two functions. One for tracking the liquid level, the other one for tracking the temperature. But other than that, you will have the same, this function will remain the same, okay? And you may call it whatever you want. So it's going to take temperature and liquid level, and it will return both of them, and you can plot. Now, let's go back to this, and here is how I can change the controller parameter. Suppose I put this as 0. What is going to happen? I can say save that. I've changed the KC, and I can go back, and before I do that, keep in mind, what was the value there? 85. The steady state value is 85, right? So let's go back and say, resolve the problem. What is it now? 100 degrees. Okay. Initially it was 80, and what was the delta T? The set point is the TR, initial condition was 80, and if I put in 550,000 joules per second, the final steady state temperature is going to be 100 degrees without any control action. Okay? So this gives you a very powerful tool for going back and changing this to anything that you want and plotting. Are we out of time? I'm sorry. Okay. So we'll continue exploring MATLAB in the next class as well. Okay.